Welcome to the 25th lecture on computational mathematics with SageMath. In this particular lecture, we will look at partial derivatives and some concepts related to that. So let us get started. So suppose you have a function z is equal to fxy. Let us assume that this function is defined on entire R2, and then the partial derivative of f with respect to x at a point AB is defined as f of x b minus f of a b divided by x minus a, the limit of this as x goes to a. In case this limit exists, we say that the partial derivative of f with respect to x at ab exists, and generally we denote it by f suffix x at ab or partial derivative, that is del f by del x at ab. Similarly, you can define partial derivative of f with respect to y at AB using f at a y minus f at AB divided by y minus b. This would be y minus b as y goes to b. So let me make this change. This would be y minus b as y goes to b. Right. So this is how you define partial derivative of a function. So this is defined using limit. So in case these two limits exist, we say that f has first order partial derivatives at AB with respect to x and y. Right. So Sage can find partial derivatives of any function, of course provided it exists, using the same function DIFF or differentiate. So suppose we have function f of x y is equal to 4xy into e to the power minus x square minus y square. Let me just show you what is this function f of x y, and let us take a point 1 comma 1, AB is equal to 1 comma 1. We want to find partial derivative of this function, that is 4xy into e to the power minus x square minus y square at AB equal to 1 comma 1. So how do we do that? So we can simply find out using DIFF, but before that let us look at what is meaning of partial derivatives. Okay, so suppose let us work with this function. Suppose we plot graph of this function and look at this first definition. So what does it say here? You are substituting y equal to b, y equal to b. So if you look at this, the plane y equal to b, this will lie in xz plane parallel to y axis. Take the intersection of that surface with y equal to b plane. That intersection will be a curve. So you are actually looking at the rate of change of the function at y, at x or along x axis, and when you intersect that surface by y equal to b plane. Okay, so that is what you can look at from this graph. So this is the surface that we just noted. This is the surface, the blue color. The red point is the point at which you want to define the partial derivative. So if you draw the tangent, this plane z is equal to y is equal to b plane, and the intersection will be a curve. So at this point you look at the rate of change of this function along this curve. That is what the meaning of partial derivative of f with respect to x. Similarly, you can try to look at partial derivative of f with respect to y at a point AB. So in that case you need to take a plane x equal to a, that is what you can see here, and intersect with this surface, and then the intersection will be a curve. So that's what you can see here, and then you at that point you look at the rate of change of this curve. So basically if you look at in terms of geometrically, the tangent to this curve at this point will be the partial derivative with respect to x, and in this case it will be partial derivative with respect to y. Right. So that's the geometric meaning of partial derivative of a function at a point AB with respect to x and y. You can plot all these things together. So both x equal to a plane and y equal to b plane together, and this is what you see here, right? Okay, so yeah, that's the two curves now here, somewhat fairly visible, right? Okay, so this is geometric meaning of partial derivatives. And how does one find partial derivatives? So in order to find partial derivative of a function with respect to x and y, you can just differentiate the function with respect to x and keep y constant. Similarly, when you differentiate with respect to y and keep x constant, then you will get the partial derivative. So for example, look at the function fxy is equal to x into y divided by x plus y, and we can find the partial derivative of this with respect to x and y using f dot diff with respect to x and f dot diff with respect to y. So this is partial derivative of f with respect to x, this is partial derivative of f with respect to y, right? And suppose for this function you can try to verify that x into fx, that is partial derivative of f with respect to x, plus y into partial derivative of f with respect to y, this is actually equal to f of xy. This is what is called Euler's formula. So we are just verifying this Euler formula because this function f of xy is a function, homogeneous function of degree 1, right? Let us look at, for example, this function f of xy is equal to 5xy upon x square plus y square and equal to 0 when xy equal to 0, 0, right? So if you look at this and try to find the partial derivative of f of xy at 0, 0, then let us see what happens. So if you want to find out first limit of f of x 0, that is the partial derivative of f with respect to x at 0, 0, you get the answer 0. Whereas if you same thing, if you try to do limit of f of xy at 0, 0 with respect to y, that means partial derivative of f with respect to y at 0, 0. In this case, the limit is again 0, and right, in both the cases this limit is 0. However, if you try to find out its limit with respect to some other curve, so for example, let us look at we can take let us say limit of this, or let us say limit with respect to x and y is equal to, I'll put 2 star x, and at x equal to 0, this limit is 2. This limit is 2. So limit along x axis and along y axis, both they are 0, whereas limit along y equal to 2x curve, it is 2. So that means this function doesn't have limit at x equal to xy equal to 0, 0. In particular, this function is not continuous at 0, 0. However, these two things, this is actually partial derivative of f with respect to x at 0, 0. This is partial derivative of f with respect to y at 0, 0. Both these things exist, whereas the function is not even continuous. So you can have a function which is not continuous at some point, but still it has partial derivatives. Okay, right. Now, if you have noticed partial derivative of a function with respect to x and y, they are actually function of xy. So you can again talk about partial derivative of f, that those are called higher order partial derivatives. So for example, let us take again the same function f of xy is equal to 4 in xy into e to the power minus x square minus y square, and suppose we want to find the partial derivative of f with respect to x at a point x comma y, then we can use f dot diff with respect to x and at x comma y. So that's the partial derivative. Similarly, you can find out partial derivative of f with respect to x at any point a comma b. That will be, so if I substitute a is equal to, for example, let us say 1.0, b is equal to minus 1.0, you will get the decimal value. Similarly, you can find partial derivative of f with respect to y at x equal to a comma y equal to b, right? If you want to find second order partial derivative, let us say first with respect to x and then again with respect to x, that's called second order partial derivative with respect to x. So this is how you can find or you could mention here 2. You can say here 2. So partial derivative of f with respect to x twice. Okay. Similarly, you can find partial derivative of x, partial derivative of f with respect to x first and then with respect to y using this f dot diff x comma y at ab. Similarly, you can find out partial derivative of f with respect to y first and then with respect to x. That is what you will get. And maybe for this function, suppose we want to check whether these two partial derivatives, they are called mixed second order partial derivatives at any point AB, whether they are the same. So you can look at partial derivative of f with respect to x comma y at AB and partial derivative of f with respect to y comma x at AB. And since these two are expressed and you want to check whether they are equal or not, you have to use bool. That stands for Boolean, right? So if I say bool this, you will get answer true. That means these two partial mixed second order partial derivatives are same. So in this case, you have seen that the second order mixed second order partial derivatives of this function at any point AB, they are the same. However, that is not the case in general. So for example, if you look at this function f of xy is equal to x power 3y minus xy cube divided by x square plus y square, one can show that this function has first order partial derivatives at 0, 0. So that's the function. Let us find out partial derivative of so first let us find limit of f of xy at first x with equal to 0 and then y equal to 0. So it's a iterative limit that's equal to 0, and you can reverse the order. This is also 0. Now let us look at suppose we want to find fx is equal to f dot diff and fy equal to f dot diff y. So that's the first order partial derivative of f with respect to x. Similarly, this is first order partial derivative of f with respect to y. Now, so these are functions of x and y. Suppose we now, if you want to look at, say what is, so I'll say show fx comma fy. So these are the as a function. So if you want, I'll put at any point x comma y, here also at any point x comma y. So these are the two partial derivatives. Both are linked. Let me use here show two different things separately. These are the two partial derivatives. Now suppose we want to check whether you can find partial derivative of this with respect to x and y. So let us see. So when we look at the second order partial derivative, we can find f dot diff of x comma y and f dot diff y comma x. These are the mixed second order partial derivatives. So these two actually it exists at any point x y other than origin. Okay, but and these two are actually going to be the same. However, at origin, if you want to find, so what you need to do, you need to find the limit of fx y equal to 0 about x at x equal to 0, then limit of fx at x 0 upon x, that's a limit of partial derivative of fx with respect to x at x equal to 0, 0. This is 0. Whereas the partial derivative of fx with respect to y at 0, 0, this is equal to -1. So what does it suggest? It suggests that at the origin, these two limits are different. That means that means this they are not the same. So in particular, what we conclude and is that the two mixed second order partial derivatives at the origin, they are not the same. However, it is same at the any other point other than origin. Okay, so this is an example of a function for which second order partial derivatives, though they exist, but they are not the mixed second order partial derivative at the origin, they are not the same. So the mixed second order partial derivative at any point are equal provided the second order partial derivatives are continuous, and these two last which we have computed, the limits are different. That is same as saying that the second order partial derivatives are not continuous. Okay. So that is why the second order partial derivatives are not the same. Of course, you can compute this limit or check the continuity of this mixed second order partial derivatives f of x y, and you can see here the limit when we take about y equal to 0 first, then with respect to x equal to 0, and first with respect to x and then with respect to y, they are the different one. So again, this mixed second order partial derivatives are not continuous, and that is the reason why the second order mixed second order partial derivatives are not equal. In case the mixed second order partial derivatives are equal, then you would have got these two mixed second order partial derivatives equal, right? So let us take one more small example. This is a function f of x y is equal to tan inverse y upon x plus y, and plus tan inverse y upon x plus x minus y, and try to show that f x, that is second order partial derivative of f with respect to x twice, plus f y, this is equal to 0. So this equation is called Laplace equation. So this particular function satisfies Laplace equation, or you can think of f x y is equal to this as a solution to this Laplace equation. This is a second order partial differential equation, homogeneous second order partial differential equation. So this is a solution of this. So verifying this is quite easy. So first define the function, and then define the second order partial derivative of f with respect to x and y, and then add these two and equate it to 0 and say bool equal to bool. This is the verification. So that's fairly simple, right? Next, suppose you are given function in let us say z, which is in terms of r and theta, but so this is in polar coordinates, and suppose we substitute x equal to r cos theta, y equal to r sin theta. So in this case, x is a function of r and theta, y is also a function of r and theta, z is a function of r and theta, and in particular function of x and y. So suppose we want to find out the partial derivative of r with respect to x, dr dy, del r del y, del theta del x, del theta del y, and del 2 r by del x del y. It should be actually del, let us find out del 2z by del x del y. So one can use chain rule for this, and let us see how we can make use of this SageMath for computing this. So first let us define z, x and y. Z is equal to r square e to the power minus theta, x is equal to r cos theta, y equal to r sin theta, and then first let us see. So the partial derivative of r with respect to x will denoted by r suffix x. Similarly, r suffix y is partial derivative of r with respect to y, and theta suffix x, that is partial derivative of theta with respect to x. This is partial derivative of theta with respect to y. So these notations we will use. So first let us declare these variables, and what we will do is, first let us say if this equation, if I look at x equal to r cos theta, that's a function of r and theta. So let us differentiate both sides with respect to x. So what will you get? First equation is derivative of this with respect to x. So left hand side will be 1, right hand side will be cos theta into derivative of r with respect to x, that is rx, and plus the second derivative of this with respect to theta, that means the minus sin theta into r, and then d theta by del x, right? Similarly, you differentiate the second equation with respect to x. So the left hand side will be 0 and the right hand side will be sin theta into dr by d theta, and plus cos theta into d theta by dx times r. So you look at these two equations, equation 1 and equation 2, and you can solve these two equations for rx dx, that is partial derivative of x r with respect to x and partial derivative of theta with respect to x. So these are the partial derivatives. So we have obtained using this the solution. Now let us store this in rx and ry as the value of this key rx, and simplify this. Trigonometrical simplify will write in simpler form. So let us ask it to show what are these things. So partial derivative of r with respect to x is cos theta, partial derivative of theta with respect to x is minus sine theta divided by r, right. Similarly, you can do you can differentiate x with respect to y and then y with respect to x, and call these equations as equation 3 and equation 4, and then solve for equation 3 and 4. This will give me partial derivative of r with respect to y and partial derivative of theta with respect to y. So let us do this. Again, we will reassign this in rx and ry and ty, and then ask it to show. So these are the partial derivative of r with respect to y and partial derivative of t with respect to y, that is theta with respect to y, right. And next we want to find partial derivative of z with respect to x, and then followed by again partial derivative of that with respect to y. That means del 2z by del x del y. So how do we do that? So we need to differentiate z with respect to y first. Z with respect to y first. That's z is a function of r and theta. So using partial using chain rule, you will have derivative of z with respect to r, that is partial derivative of z with respect to r, times the partial derivative of r with respect to y, plus partial derivative of z with respect to theta times partial derivative of theta with respect to y. And if you simplify this, this is what you get. So let me print z underscore y. That's the first order partial derivative of z with respect to y. Now find first partial derivative of zy with respect to x. So that again you can do using chain rule. This is the final outcome, right. Now let us define what is meaning of directional derivative and gradient. So if you have a function z is equal to fxy, and suppose you take unit vector u, u1, u2, then the directional derivative of f at a point a, b, which we call the point as p is equal to ab, in the direction of u is given by limit of f of p plus hu minus f of p divided by h. So what you are looking at is numerator is change of the function value along u, along the direction u, and then this is the rate of change of f at p in the direction of u. That's called directional derivative of f with respect to u at ab, right. So this you can expand p u as u1, u2. This is what you get in terms of coordinates, right. So suppose you have this function f of xy is equal to 4xy into exponential of minus x square minus y square, and you can find out its directional derivative at a point 1 comma 1 in the direction of, let us say, 1 by square root 2 comma 1 by square root 2. That's a unit vector. So this is going to be minus 4 into square root 2 into e to the power minus 2. Now this directional derivative, actually you can check that the directional derivative of f at ab in the direction of u can be written as partial derivative of f with respect to x at ab times u1, the first coordinate, plus partial derivative of f with respect to y at ab times u2. So let us just so one can use this formula to also find partial directional derivative of f at any point ab, and you can see that using definition whatever we got is same as what we got using this formula, right. Similarly, you can define gradient of a function. So gradient of f at ab, this is denoted by nabla f ab. This is read as nabla or del f at ab. This is the first coordinate is partial derivative of f with respect to x at ab. Second coordinate is partial derivative of f with respect to y at ab, and then there is a relationship between directional derivative and this gradient. So directional derivative of f at ab in direction of u is actually dot product of gradient with u, right. So let us look at the gradient of a function. You can find using f dot gradient and at any point a comma b. So this is the gradient, and it is a vector. Gradient is a vector, and you can verify this. So v dot, that is dot product of v with respect to the vector u. So this is u is a as a vector, you can define like vector u1 u2 that give the coordinates. So you should be able to see that this is the directional derivative of f with respect to in the direction of u at AB, right. You can look at what is geometric meaning of gradient of a function. So the gradient of f at AB is actually a direction in which the function increases with maximum speed. Similarly, the negative of the gradient is the direction in which the function decreases with maximum speed. So that's the geometric meaning of this. So one can very easily show these two things. It is quite easy. It's a very simple problem. One can convert this into one variable optimization problem, one variable problem of maxima minima. And the second thing is, if you look at the tangent to the level curve, if you look at any level curve z is equal to, let us say, c, that means you are looking at f of x y equal to c. That's the level curve at z equal to c. And take any point on the curve, let us say AB comma f AB. At that point, if you look at the gradient, it is orthogonal to the tangent, right. So this is what is the meaning. Tangent to the level curve, this is orthogonal to the gradient at AB. So let me just demonstrate this for this function. So f of x y is equal to x square minus 2xy plus 5y square plus 3x minus 2y plus 2, and take any point, let us say AB, and at this point let us draw. So this is the level curve. The blue one is the level curve of this function. This is the point on this level curve, this red one. This is the red one is the tangent, and this is the gradient. So you can see here they are perpendicular. And it doesn't matter, you can choose some other point. Instead of 1 1, let us choose minus 1 comma 1, and it will be the same thing. Instead of minus 1 comma 1, let us choose minus 1 comma, let us say half. Again it is the same thing. Or you can check minus 1 comma minus half. So everywhere this is true. Okay. So similarly, you can draw the contour of the function and plot the gradient as a vector field. And when you plot this, let us see what it means. So these black curves, they are the gradient. And for example, if you look at this particular curve, this is the level curve at z is equal to 0.6, and these arrows are the gradient. So you can see here also this gradient is perpendicular to the tangent to this particular curve. So that is another way to explain the gradient is perpendicular to the level curve, right. Okay. So next let us look at how to define tangent to a surface z is equal to fxy. So the equation of the tangent plane at any point AB is given by Txy equal to f of AB plus partial derivative of f with respect to x at AB into x minus a plus partial derivative of f with respect to y at AB into y minus b. So let us again take the same surface and try to plot the tangent. So fxy is equal to 4xy into e to the power minus x square minus y square. AB is again 1 1. Find out fx fy at AB and then define the tangent, and then let us see what is the tangent plane. The equation of the tangent plane is this, that is z is equal to this is the equation of the tangent plane, and one can try to plot the graph of the surface along with the tangent plane. So that's the graph of the tangent plane at this particular point. So that is again quite easy to plot. You need, once you have defined the tangent plot, then you just use plot 3D to plot the surface, point 3D to point to plot the point, and again plot 3D to plot the tangent plane, right. So next let us look at how we can define Taylor's polynomial, right. So we have already looked at how to find Taylor's polynomial of various degree at some point for one variable case. The same function can be used for more than one variable. So if I have the same function f of xy equal to 4xy into e to the power minus x square minus y square, and if you want to find Taylor's polynomial of f at AB of degree 3, then what you need to do is f dot Taylor x comma a, that is at x at a, and this y comma b, that is y at b, and this you mention the degree. For example, if I look at 1, then this is first order Taylor's polynomial. This will be nothing but the tangent plane, right, the first order approximation. If I mention here 2, then it will give me second degree Taylor's polynomial in xy, and this 3 will give me third degree Taylor's polynomial of fxy at x equal to 1 1, and you can even try to plot the graph of the surface along with the various Taylor's polynomial. So for example, if you look at the function f of xy is equal to cos x into cos y, and let us take the point 0 0 at the origin. Let t1 is the first order first degree Taylor's polynomial, t2 second degree Taylor's polynomial, t3 is third degree Taylor's polynomial, and let us try to plot the surface along with all these Taylor's polynomial, and then you will see here. So the red one is the tangent plane, actually first order Taylor's polynomial. Second order Taylor's polynomial, in this case the point is actually local maximum, so it will be very close to the actual function, and the yellow one is the third degree Taylor's polynomial. So you can take the various function and try to approximate. You can go to higher degree, and then you will see that higher degree Taylor's polynomial at any point will be very close to the graph of the surface. So that is the demonstration. Again, let me leave you with a few simple exercises. So the first exercise is, look at this surface, try to plot the contour and gradient, and then demonstrate that the gradient is perpendicular to the tangent to the contours, and these two are to find the limit if it exists. Then show that this function satisfies the Laplace equation. This is a function of 3 variables. Plot this surface along with the tangent plane at this point. Look at this function z is equal to x square y plus 3xy square, and let us take x equal to sine 2t, y equal to cos 2t. Find dt by dz by dt. That's a chain rule at t equal to 0. And then the next one is, find the directional derivative of this function at this point in the direction of 2 comma minus 5. So this means this is the direction, so you have to convert this into unit vector. So you have to divide this by length. In the next problem, which is the last problem, is suppose the temperature at some point is given by Tz, T of xyz is equal to 150 into e to the power minus x square minus 2y square minus 5z square. T is measured in degree Celsius and xyz are in meters. So find the rate of change of T with respect to in the direction of this at this point. So this is nothing but directional derivative of T at the point P in the direction of this. Similarly, find the direction V in which the temperature increases with maximum speed. So that means you have to find the gradient, and also find the maximum rate of increase of T at P. That means you have to find the length of the gradient. So these are the simple exercises. I am sure it will be quite easy for you to solve. Okay. So thank you very much. Next time we will look at application of partial derivative as finding local maximum, local minimum of function of 2 variables. Now let me just at this stage make a comment that whatever we have done for 2 variables, finding limit, checking continuity, finding partial derivatives, and various concepts like directional derivative, gradient, etc. All these things can be extended to function of more variables, and exactly the same functions of Sage can be used. Okay, so thank you very much.